were discussing how data path and control paths can be together designed in complex digital systems. So, if you recall, in our last lecture we gave a simple example of a multiplier, an unsigned multiplication algorithm which worked on the principle of repeated addition. So, we take a few more examples so that the methodology becomes more or less clear to you. How do we do it? So, we continue with our discussion, data path and controller design part 2. Now, just one thing, you recall in the design that we discussed in the last lecture, we had designed the data path, we had designed the control path. Now, if you recall the way we had designed the Verilog code model for the controller, there we had used one always block which was activated by the clock, which was carrying out the state changes depending on the input conditions. It was checking the input conditions, based on that it was going to the appropriate next state. And in another always block which was based on blocking statements, there we were generating the control signals for the data path. Now, here we shall talk about an alternate way of implementing the same thing. So, this in fact is a, you can say, a better style of modeling. So, the difference is as follows. As I said in our earlier example, the always block which was activated by the clock. So, the inside that always block, so we were manipulating the calculation of the next state as well as we were assigning the next state. Both the things were performed in the same block. Now, what we say here is that a better and recommended approach may be, so you use a simpler always block which will only trigger the state changes. So, it will not make any calculation or computation as to what the next state will be, and in one or more always blocks, separate always blocks, both of them will be using blocking statements, blocking assignments. So, here you compute the next state as well as you generate the control signals for the data path. So, in this lecture we shall be taking another example, namely that of computing the GCD of two numbers, greatest common divisor, and we shall first be following the previous approach what we did in the last example. Then we shall see how this new proposed method that we are talking about, how we can make the design modification to incorporate this, right. Okay. So, the problem that we consider here is GCD computation, greatest common divisor. Now, you recall the GCD of two numbers is defined as the largest integer that divides both of them. For example, if you have one number as 26, one number as 39, and if you compute the GCD of them, GCD will be 13, because 13 is the largest number which divides 26 as well as 39. Now, the method we follow is the method of repeated subtraction. So, the algorithm is depicted in this flow chart, you can see it is very simple. So, you read the two numbers for whom you are trying to compute the GCD, then you compare A and B. If A is less than B, then subtract A from B, compute B minus A, store the result in B. So, if you see A is greater than B, then you subtract B from A, and if you find that equal, then you have already got the result. Okay. So, let us take an example. Well, 26 and 39 may be too simple an example. Let us take an example of 26 and let us say how much 65. 26, 65. Okay, here also GCD is expected to be 13, because both 26 and 35 is divisible by 13. Now, the method we follow, so we use that same method. A, let us say, is 26, B is 65. So, in the first step we see B is greater than A, subtract A from B. So, if you subtract 26 from 65, it will become 39. Then again compare, again B is greater than A, subtract A from B, it is now 39 minus 26 is 13. Now, again compare A and B, now A is greater, subtract B from A, it becomes 13. So, now you have a situation where both A and B are equal. If A and B are equal, then either A or B will be the required GCD. This is the algorithm, right. So, we have actually used a simple algorithm like that. So, as before, here also we shall be identifying the functional block that will be required in the data path and identify the control signal and design the FSM to execute this in sequence. Okay. Now, if you look at this flow chart, you can identify what are the elements in the data path that are required. First, you will have to read the two numbers A and B. For them, you will be needing two registers. Then you need subtraction, so you need a subtractor. But one thing you see, sometimes you are doing B minus A, sometimes you are doing A minus B. So, even if you have a single subtractor, the two inputs of the subtractor must come through a multiplexer. So, you will have to select either A or B, depending on whether A is less than B or greater than B, one of them will be coming to the input of the subtractor. Okay. And finally, to carry out the comparison, you need some kind of a comparator. You need a comparator circuit also, and of course, lastly you will have to output the value. So, let us see the overall data path as I have said. So, we will need two registers A and B to store our initial numbers. Then as I said, we need a subtractor. The first input can be of the subtractor can be either A or B, that is why we have used a multiplexer with the inputs coming from A and also from B. For the other input also there is another multiplexer, input coming from A as well as B. There are select inputs of these muxes, cell 1 and cell 2, they will select which one of A and B are selected. If select 1 is 0 and select 2 is 1, then here A will be selected, from here B will be selected. And here there is a comparator which will be comparing the values of A and B and will be generating the three status signals less than, greater than or equal to. And there is another multiplexer. This multiplexer will be either selecting an external data signal, data in. You see, initially when you load the values in A and B, we need the data in to come to the bus and be loaded to B or to A. And for loading, we have this load A and load B control signals. And this select in control signal of the multiplexer will select which of the inputs are selected. And during the normal computation after subtraction, the result will have to be stored back into either A or B. For that, I will have to select this input of the multiplexer, this sub out will be coming to the bus and we will be selecting again either load A or load B. Okay. So, this is how the data path functional components look like, and you can also see the control signals load A, load B, select 1, select 2, select in, and these are the status signal which are generated by the data path less than, greater than and equal to. So, the outputs of the multiplexer we are calling as x and y. Fine. So, schematically data path treated as a black box, as I said, these are the 5 control signals which are required and these are the 3 status signals which it is generating. So, we will now have to design the control path in a similar way as you saw earlier. So, for the control path there will be a clock, of course, the data in which will also come to the data path, and there will be a start signal which will initiate the computation of the GCD, and after it is done, the done signal will be activated. Okay. this is the signals for the interface. Now, let us come to the control path. Now, that same flow chart we are just showing in a slightly different way, stepwise. From the beginning, let us say we load the data in signal which is coming from outside into A first, then data in into B first, next we are calling them as states. S0 is the initial state, this is state 1, this is state 2. Then we compare the outputs of the A or B register which we have called as A out and B out. If it is less, then B out goes to X and A out goes to Y. What does this mean? You see, B out goes to X and A out goes to Y. That means, I am selecting these multiplexers appropriately. Similarly, if it is greater, the other inputs are selected, A out goes to X, B out to Y, and the result goes back to B or to A. And if they are equal, the result is already in either A or B and you are activating done. This state is S3, S4 and S5. So, in terms of the state transitions, so we can depict this like this, starting from S0. So, whenever start is activated, we go to S1, then to S2, then from S2, depending on the condition, 3 conditions are there. If it is less than, we go to state S3, if it is greater than, to S4, if it is equal, we go to, you see this red arrows indicate the equal to conditions, equal to, it goes to S5. Similarly, when you are in S3, see after S3 you again go back, okay, like this. So, you can again come to S3 or you can come to S4 or you can come to S5. So, from S3 again, if it still remains less than, you remain in S3, if it is greater than, you go to S4, if it is equal, you finally go to S5. Similarly, for S4, if it is greater than, you remain here, if it is less than, you go to S3, if it is equal, you go to S5. So, this FSM we have to implement. So, here we are showing the FSM implementation using the approach which we showed with the previous example first. So, we are first defining the data path, where these are the signals GT, LT, EQ are the output signals, and all the others, these 5 are the select signals, and of course, data in and clock are there. These are the control signals, and load A, load B, the multiplexer select and clock are the input signals. Data in, I am assuming that it is a 16-bit data, and these are outputs. And these intermediate signals A out, B out, X, Y, bus and the output of the subtractor, these are all assumed to be 16-bit buses of type wire. Now, just in the schematic we have seen, we use 2 registers A and B, 3 multiplexers, 1 subtractor and a comparator. So, we have just instantiated that many functional blocks here. Parallel in, parallel out is a register we have already defined, I will show it. So, here A out is the output, bus is the input, load and clock are the control signals. Similarly, for PIPO B. For the multiplexer, this X is the output, A out, B out are the inputs and select 1 is the select. Similarly, for the second multiplexer. For the third multiplexer, bus is the output, sub out and data in are the inputs and select in is the select. And there is a subtractor where sub out is the output, X and Y are the inputs, and there is a comparator finally, less than, greater than, equal to the outputs, and these are the 2 input numbers. Right now, a very quick look at these descriptions. People here, for the sake of convenience, I am shown all of them in a behavioral fashion, but in a real design, when your target is to achieve higher performance, we often design many of the modules in a structural way, so that we have entire control over the way this circuit is designed. Because here, when you design using behavioral fashion, we leave it entirely to the synthesis tool to decide what kind of circuit it will be generating, right. Okay. So, you see, first the register, the parallel in, parallel out, data in, load, clock, it is very simple. data in is the input, load clock are single bit control signals. So, always at passage of the clock, if the load signal is active, then data in goes to data out, it is loaded. Subtractor is a combination circuit, very simple. This in 1, in 2, out are all 16 bit numbers. So, the whenever anything changes, always at star, out equal to in 1 minus in 2. Comparator is also very simple. Data 1 and data 2 are two 16 bit numbers, and these are the outputs. We have used 3 assign statements. Assign LT equal to data 1 less than data 2, which means if this condition is true, that condition will be stored in LT. Condition true means it is stored as 1. So, 1 will be stored in LT. If it is false, 0 will be stored. Similarly, for this one, if this condition is true, 1 will be stored, otherwise 0. Similarly, equal, right. Mux also is very similar. This is actually a set of 16 2 to 1 multiplexers, because we are multiplexing 2 inputs in 0 and in 1, each of them have 16 bits. So, actually these are vectors out, in 1, in 2, depending on the select line, we are either selecting in 0 or in 1. Okay. Now, the controller. The controller again it will be generating all the control signals for the data path, done, clock, and less than, greater than, equal to and start are the signals which it is taking as input. These are inputs, and the signals which it is generating for the data path, these are outputs, and because you are using a procedural block, you have declared them of type range. Now, in this example, because there are 6 states, we need a 3 bit state vector. So, we define it as a 3 bit state vector called state, and using parameter we call these states as S0, S1, S2, S3 and S4 and S5. Okay. Now, in the first always block triggered by the clock, we are just implementing that flow chart whatever I had shown. So, initially we are in state S0. If start is active, the state becomes S1. Well, if you are in state S1, irrespective of anything else, next state will be S2. Well, if you are in S2, then if it is equal, go to S5, if less than S3, greater than S4. Same thing is done for the states S3 and S4. And whenever you are in state S5, that means you are done, you remain in state S5. Well, and initially if the state is not initialized, so there is a default case which initializes state to state S0. This is for the state calculation. Then there is another always block which checks the state. Whenever the state changes, there is a case statement and it selects the appropriate control signals. You can actually verify. Well, in S0, well, so while you are going from S0 to S1, you will have to load A. So, that is why load A is active. You are selecting the other input of the multiplexer select in, so that data in gets into the bus, while load B and done are 0. And when you are in S1 going to S2, you have to load B. So, load B is 1, again select 1 is 1, and here when you are in S2, S3 or S4, it is the same. You check the conditions. If it is equal, you activate the done signal, else if it is less than, then you select B in the first one and A in the second multiplexer, load B, result will go back to B, and else you select A in the first multiplexer, subtractor the multiplexer, B in the second multiplexer, you activate A, result will go back to A. Similarly, S3 this is same, and in the same way S4 is also same. Okay. And finally, in S5 when you are done, you activate the signal done equal to 1 and deactivate all the select lines and loads, so that nothing else will proceed after that. And for default we are just setting load A 0, load B 0. So, you see in this example the FSM, we are actually generating all the control signals as per the flow chart whatever you require. Well, whenever you want to select a multiplexer, one input of the multiplexer, we are activating cell 1 and the select 2 control signals accordingly. When you have to load the result into A or B, we are activating either load A or load B. So, you can just compare that flow chart with this means FSM description, and you can see the correlation, they are the same. Okay. Fine. So, to test it out, we wrote a very simple test bench. So, again we instantiated the two modules, GCD data path and the controller. This is the clock generation. Initially clock was 0, and at time 3 we activated start, and simulation continued till some time 1000, and after every 5 the clock was toggling. So, the clock period was 10, and these are the two input data we are applying at 12 and a little later after 1 clock, 143 and 78. Well, if you just do it manually, the result is supposed to be 13, and we are monitoring the time as well as the A outs. You see, this output of the A register is not available here directly, but we have instantiated these modules dp and con. Well, we can write like this: dp dot A out means this A out is a signal which is defined inside the dp module. Okay. So, we want to see this because here the result will be there, and of course, done, and this dump file and dump variables we are generating here. So, if you just simulate this, the result comes like this. So, the three things that are printed are time, the value of A, output of A, and done. So, A changes and finally, it stops at 13, which is the final result, when done also becomes 1, right. And just a simulation snapshot also is shown here. So, here also you can see the different signal values: clock, A out, B out, bus, load A, load B. So, you can see the values of A out and B out are changing. You see, initially the values are 143 and 78. So, 143 means 8f, 78 means 4e. So, 8f minus 4e, it becomes 41, 4e minus 41, it becomes 0d, 41 minus 0d becomes 34, 34 minus 0d is 27, 27 minus 0d is 1a, 1a minus 0d is 0d, they are equal. Now, you stop. Done gets activated here when they are equal. So, the result is 000d, which is 13, right. Fine. Now, the alternate approach that we were talking about, let us quickly see that how our design will look like if we use the alternate approach. There is not much difference really. There are two things we have to do. So, in the earlier case, we had defined only one variable that was storing the state vector, but now we will be storing two different state variables. One will be the present state and other will be the next state. Now, in the clock activated always block, we will only write present state equal to next state. Whatever was next state in the last time, it will become the present state now, and in the other always block we will do all other computations. Let us see. So, our main always block becomes very simple. You see here, as I said, we have defined another variable called next state. The other part is same, the header does not change, and in the first always block is very simple now here. It only says state equal to next state, and the next state is calculated in the second always block. So, here earlier these red things were not there, the remaining control signals were there. Now, we have made a little modification here. We have also added the statements which compute or calculate the next state. So, when you are in S2 and it is equal, your next state will be S5. When you are in S2, it is less than, your next state will be S3. If it is greater than, next state will be S4. So, in a combinational block using blocking assignments, you are doing this. So, same thing in all the cases. So, you see there are two always blocks which are running in parallel. One will be a clock controlled thing, which will, whenever clock comes, it will just put the next state into state, and in the other block which is not clock controlled, which is controlled by state. Whenever state changes, you do it. So, whenever there is a change in state, you make some modifications there, generate the control signals and also assign the proper value to the next state. So, that whenever the clock comes, the first always block will go to the correct next state, right. Fine. So, actually this is how this design is carried out. So, with this actually we come to the end of this lecture. Well, if you see, this example was quite similar to the previous example. So, we deliberately we are taking a few examples, so that you become familiar with the process of design. Given any problem, you see these problems are not very trivial, a little complex. Of course, real digital systems can be much more complex, but still just to have a flavor of complexity, we are taking some reasonable size problems which can be discussed and put on the slides, right. So, in the next lecture also, I mean here next we shall be talking about another example. There we shall see that how we can carry out signed multiplication using a well known algorithm. Okay. So, that we shall see in the next lecture. Thank you.